All right, so in this video, we are going to sort of like collect the skills that we've gathered related to sequences and in some sense tie it all together. And we can do this by expressing the general term of a sequence. Now remember, we've seen examples of what a general term looks like. So from the past work that we've done, when we have something like an equals n over n plus 1, this is essentially a functional expression, which allows you to simply plug in n and then quickly assess what like a 10 or a 100 would be. So when we ask to find a general term, we're essentially looking for a functional expression, which allows you to quickly plug and chug to determine what a sub anything would be, what the 26th number in the sequence would be. Like in the example, we had an equals cosine n pi. Well, if we want the 26th number, we could just plug in n equals 26 and find that. So what we're seeking here in this example is for the sequence that we provided a general, or that we've been provided a general expression functionally. Well, we've been provided a sequence that has a first number of 2/3. And that has a recursive definition for the next number. The next number is 2 times n plus 1 over n plus 2 times the previous number. Well, as we've seen with the recursive definition, this is going to allow us to find what, for example, a2 is. It's subsequently going to allow us to find what a3 is and so on. Well, what would a2 be? Let's think about this. Well, we could take our recursive definition and plug in n equals 2. And if we would, we'd get a2 equals 2 times 3 over 4 times a1. Well, a1 is, as it turns out, 2/3, so we could plug that in. Okay, now what about what would a3 be? A3 would be 2 times 4 over 5, plugging in n equals 3 times a2. What would a4 be? A4 would be 2 times, plug in n equals 4, 5 over 6 times a3. A5 would be 2 times 6 over 7 times a4. Okay, now, why write all these out? Well, because if we're going to write out a general term for our sequence, we kind of need to see what the pattern is. So we've got 2/3 here as our first number. Well, once we know that the first number is 2/3, we can multiply by, 2 times 3 over 4 to get ourselves the second term in the sequence. When we multiply, you can see here that the 3's cancel, and I get 4 over 4. Okay, sweet. So the second term in our sequence is 4 over 4, or, well, frankly, just 1. So when we come down here and we see that a3 is this fraction times the second number in our sequence, well, then that's just this number times 1, because 1 is the second number in our sequence. So multiplying this out, this fraction times 1, that's 8/5. So now we know 8/5 is the third number in our sequence. If you start to look at the terms that are appearing in our sequence, you might already be able to notice a pattern. Note, the numerators go from 2 to 4 to 8. You might speculate what the next numerator is going to be. The denominators go 3 to 4 to 5. Again, you could speculate what the next denominator is going to be. Well, to validate if this speculation is going to hold, we need to find what the next number is, namely a4. Well, you can find the fourth number in the sequence by taking this fraction times the third number in the sequence. The third number in the sequence is 8/5. Here as well, the 5's cancel, and we simply get 16 over 6. And if you were thinking the same thing I was thinking, that the numerator was doubling and the denominator was increasing by 1, then, we're seeing the pattern. And we can now know precisely what the next term would be, 31 over 7. And, because the numerator is 2 times and the denominator is 1 more than the previous. So now, what do we need to do? We need to ultimately get an expressed where everything that's over here on the right-hand side is just in terms of n. Well, when you think about this here, you know that an is going to pop out to be a fraction. And what's upstairs is, as we can see, a multiple of 2. So in particular, what's upstairs here, 2, is just 2 times whatever n is. Note, 4 is 2 times 2. 8 is 3 times 2. maybe it's not what n is times 2, maybe it's 2 to that power. That's probably a better way to say it, because 8 is not 2 times 3, 8 is 2 to the third, and 16 is 2 to the fourth, and 32 is 2 to the fifth. So the numerator is always 2 to the nth power, corresponding to whatever term you're in. So if you were in the sixth term, the numerator would be 2 to the sixth, or 64. If you're in the 10th term, the numerator would be 2 to the 10th. What about downstairs? Downstairs is purely a number that's increasing by 1 each time. So as you can see here, when n is 1, we get a denominator of 3. When n is 2, we get a denominator of 4. When n is 3, we get a denominator of 5. Now, how can you get from 1 to 3, 2 to 4, 3 to 5? Well, you can get there by adding 2 to whatever your n is. So downstairs here, whatever pops up downstairs, like 6 in this example, is just 2 more than 4. 7 is 2 more than 5. So the denominator here would be 2 more than n. And as you see, looking at this form, this expression here is now stating the general term of our sequence, because you want to know the sixth term in the sequence? It's just 2 to the sixth over 6 plus 2. And note, this expression does not depend on the previous term. No, this expression is merely plug and chug. So a 25, 2 to the 25th over 25 plus 2. In general, we found precisely what an is.